John is going to talk about gaps in knowledge and turn it over to Professor John Straube. Thank you.
Thank you, Joe. Great to be here, period. Great to be asked to speak again. It is an honor. Even though I've been associated with this thing for a long time, this event is a pretty big deal. And there's some, great colleagues here, great friends here, and Joe is the epitome of both of those things brought together. Cynical bunch of people. But after this morning's, I would say, serious stuff that we're talking about, like people dying in various horrible ways and losing their scrotums, I would like to talk about more my stuff, which is moisture, water. I was told maybe I should talk about how you can use raindrops to dehumidify a space and how you get condensation on raindrops, but I'm not going to. So instead, I'm going to talk about capillarity and how it kind of works in a rather narrow group of examples. Now, I am also recognize that I had to have dog pictures in the presentation, so I managed to update this over lunch. And so this was you folks only half an hour ago. Right now, I want you to be like this. I am paying rapt attention, and in the next hour, I want you to do that. When I point out some of the physics behind everyday moisture events. So I'm going to talk about capillary or capillary forces. I'm told it's one or the other. We're going to apply this to drainage of walls, leakage of windows, ray penetration. And my focus, other years I've talked about pores and how water is wicked into, say, brick or wood. And those are tiny pores. We're going to look at the comparison and why it's actually different when we get a little bit bigger. And that transition is what matters from a building science point of view. So I actually gave a size range there, 0.02 inches to 0.5 inches for very important reasons. This remote control is not very remote. So yeah, capillarity, been around for a long time. One of the drivers behind this presentation was that it's actually some legal work that I was doing, and I assumed that experts testifying in a legal case would know about capillarity and would know which direction it acted and the relative magnitude. And I was a bit surprised and taken off guard that they didn't. And so when you make an expert opinion, even if you're wrong, the judge has to weigh that. So, people would say things about capillarity that you could prove were wrong by going to Wikipedia, but it doesn't matter if they're an expert. And so I was a bit surprised at how not widely understood some of this stuff is. So that's why, even though it's been around forever, and I think that's maybe why, because things that are done a long time ago, people forget because you can't find them on Google. And some of them even they still have this stuff. You have to go to like a place where they store piles of paper. They call them libraries. And you even have to look at them. And so this is a major obstacle for many people in learning stuff. And so a big part of we've done this a lot, we call it our Alexandria project, actually Alex Lakachko coined that, about scanning really good research, putting it digitally online, because then now it exists again, right? So the last person's name on this list, James Jurin, is actually one of the people who is most often given the name to the law that I'll describe to you for capillarity. But the problem with James Jurin is he just proved and identified capillarity and showed its significance. But the person who put math to it was two people, Laplace and Young, and so oftentimes that's the people who get named. They did nothing about really capillarity experiments, and what they added to it is a mathematical understanding. So that you might hear that name sometime. So
just going to quickly talk here. Well, I always talk quickly, I guess. I'm going to have a short chunk where I talk about background science. Oh, that was a bit faster than I had intended. So the water molecule, just to recollect, for those of you here in 2018, the special thing about this cockeyed Mickey Mouse molecule is that the ears are a little bit positive and the body is a little bit negative. And it's because that makes one side of the molecule a little bit negative and one side a bit more positive, we call this a polar molecule. It has poles. And it really influences how things behave. And things like the way water sticks together massively influences huge effects all across the sciences, etc., including very much in the medical sciences. But there's two forces that we want to look at when we talk about how water molecules interact, how water molecules stick to each other, how they're attracted to each other, called cohesive forces. Those polar molecules, the negative sticks to the positive sticks to the negative, and we end up with liquids that have viscousness. That's a word. Some of you looked a bit dubious, but no, it is a word. But it also brings up the surface tension thing. So if we look at the Canadian molecule here, that would be the one labeled A, in the middle of the fluid, it is attracted equally to the molecules all around it. And so the forces that are distributed equally in all three dimensions around it. As you move to an interface between water and, in this case, air, but it could be alcohol, it could be helium, depends. But for building science, it's water, maybe a little alcohol. The surface, it actually has no molecules above it to connect to. So it has the same positive and negatives and same desire to be attracted to stuff, but there's nothing up above. So it grips more strongly to the ones that are beside it. And this creates what people have often noted, like a film on the water. And that strength of that film is called surface tension because it's a tension force. That's how we measure it. It's harder to measure compression because the water just goes blurp. That's the noise it actually makes in a microscope. But the tension is something that you can measure. You don't believe me, do you, Achilles? You do, yeah. You've seen the microscope. It doesn't blurp. So the surface tension, I think everyone knows. That's why we can float a pin on the water, or that's why these bugs can float on the water, because there's enough surface tension. And the way you measure this in real life in a lab is you get a platinum circular ring, a little wire made of platinum, and you set it in the water, and then you pull up on it and you measure how much force it takes until the ring breaks through. And you measure the length of the ring and you figure out the force, and the answer is 0.072 newtons per meter, and you don't care. And you shouldn't care. I'm just telling you there is a number. Water is also attracted to other materials. It's not purely narcissistic and attracted to itself. It is also attracted to materials, but not all materials. It's attracted to all water molecules, but not all materials. So some materials are water-loving, and they're called hydrophilic, coined by Achilles, that's why it's Greek. And hydrophobic means they're water repellent, another Greek term. So when we look at adhesive forces, you'd say those are adhesive forces because the water's stuck to the vinyl siding. But actually the reason they make droplets is because of the cohesive forces that hold the droplets together. They're stuck to each other and they're stuck to the underside of the vinyl siding. And both forces are actually going on at the same time there. Now, the way we describe materials that are water-loving, hydrophilic, you measure it, right? So obviously, we have to measure it to be scientific about it. And so you put a droplet on the surface, and if it flattens out with an angle of less than 90 degrees, we call it hydrophilic. It's actually a little bit more complicated if you do this, because if you put a very small droplet, it does tend to be kind of flat. And as you make the droplet bigger, it bulges up until it starts to flow. It's just before it starts to flow after you're bulging it up. That's not what it says in the ASTM standard. That's the actual angle that you're supposed to look at. So if it's hydrophobic, like a waxed car surface is, right? You're using wax, maybe people still wax their cars. And when water droplets, they form more blobby like that. So this is action photography, where a water droplet is just impacting onto a fiber cement sheet. So the sheet, like many building materials, is water loving. Wood, gypsum, brick, concrete, fiber cement, they're all water loving, and you know, it's sucking the water in. In fact, it's hard to make a droplet because the water is being sucked into it. Now, this is same fiber cement sheet, but now we've coated it with an acrylic coating that provides aesthetics, but it also provides water repellency. And here, not only does it stop water from being absorbed, it also means that you can see the droplet, right? It's hydrophobic as much as they can. So many people get excited by hydrophobic coatings because they're going, like, really, if all I needed to do is cover my jacket with hydrophobic material or my building, water wouldn't leak in. And that's true in theory. In theory, communism works. And in practice, there's little bits of dirt that accumulate on real life surfaces. And so even though we can make in the lab quite hydrophobic materials, applying them in the field is always balanced by the fact that eventually there's dirt and it changes them. So there's a limit to how far we can get in hydrophobicness in real building materials. It's a little bit like reflective coatings or white roofs. You can paint really, really white roofs, but unless you have really, really white dirt, the reflectivity doesn't remain the same. And so we pick a lumber that's higher than what it is in the lab. If you're lucky, you can live even better. You could live in a place with shiny dirt. So if you have shiny dust, it'd be great to have like reflective roofs. But we have dirt that isn't hydrophobic, and it means that there's limits. Now, if you're doing science, I'm putting quotes around it because I don't really do that, but if you're doing science, you put water on, and glass is a commonly used material. Well characterized, and the silicon dioxide, which glass is, silicon dioxide makes up many mineral-based materials. There's a lot, like concrete, for example, but gypsum and bricks, etc. There's a lot of silica in some of these products. So it's often used as a surrogate for mineral-based building materials in studies. So here's a water droplet put on a piece of glass, and it's increasing, it's made larger and larger by 1/10 of a milliliter or less at a time with a hypodermic needle and a syringe, until it starts to flow. And so there's an angle measurement there. There are more sophisticated ways to do this properly. I'm showing you this because this is the water and the glass that I'm going to use in subsequent experiments. The reason the water is blue is because I put food coloring in it. Water isn't actually that color. Just saying for the first timers, the crowd, you would have learned that if you'd been here before, but no. So that blue, now that is a flashing material, a peel and stick flashing material, which are often either butyl or bitumen, SBS bitumen, with a facer of some sort of polymer, often HDPE, sometimes there's scrims of polyester. This happens to be high density polyethylene, HDPE. There's various types of PE's facers, and it is quite water repellent, as you can see from my bulging droplet. I wouldn't just show anybody a bulging droplet of mine. So one of the things we learn is it's not just the dirt that matters, but also if I take the droplet and tip it on an angle, I think you can visualize in your head that the front of that droplet has a steeper angle than the tail. And this is a real test. I mean, people really do this with sheets of glass and very carefully calibrated equipment to find out what the angles are, and that's how you are properly supposed to characterize a material's surface response to water. So I'm telling you that there's an angle with that, that you should say is wettable or not, but actually the angle varies. And people who are measuring this stuff will honestly find out that it varies depending on which track it takes down this sheet of glass. And the glass you're looking at is actually, it's lab glass. That means it's more expensive. But it also means it comes with a sheet that says what's in the glass, right? So you know what it is, but it's flatter than normal glass. And even so, when I put a droplet and run it down the surface, the droplet will have a different angle as it moves down by a little bit. So all of this is to say, like many times in building science, getting obsessed about the decimal place is a waste of effort, right? This is a game of hand grenades. You just got to throw it in the right direction. We're not really looking at marksmanship here. So although most of this stuff had been written down in papers that you can't even find in our library, my university was founded in 1957, there are papers that are done often in obscure areas of research where they are reinventing the capillary science. This is actually a very useful one. It comes from the School of Dentistry. And that's because capillarity, we have a lot of water in our bodies, apparently $1.63 versus minerals, but we're actually probably 70–80% water, and so a lot of understanding how water moves around stuff. And in dentistry, you can imagine how they're all about cracks, right? And they don't like cracks, they don't like holes, they want to fill up cracks and holes, and so capillarity is an area of real interest to them with different materials. So they did some pretty interesting research in this paper, and one of the things at the bottom where it's labeled table II, which is 2 in modern language, it shows with different materials. So it's not just water and glass, it's water with acrylic, water with silicone, water with Teflon. Teflon, if you may be not surprised, is highly hydrophobic. So if in my lab, if I wanted something as a baseline for hydrophobicity, you'd get a sheet of Teflon, like good quality Teflon, and it really beads up. It does a really great job. So most WRB materials are hydrophobic-ish. That isn't a word. And so you can see, this is from Dr. Nathan van der Bosche. Some of you may know him from Belgium, does a lot of good building science research. Static angle, advancing angle, receding angle. I like the honesty where he's doing the plus or minus 4 and 3, like he also in the paper tells you I measured this 16 times or 24 times just to, whatever, it varies a bit. So polycarbonate, Lexan, it would be a trade name, is quite hydrophobic, but cross-woven polyethylene wrap, not quite sure what they're meaning, but I think they mean the textured, usually polyester. And then the spun-bonded polyethylene, probably Tyvek, right, Teresa? Probably Tyvek. And then when they say spun-bonded polyethylene grooved, well, then it's almost certainly Tyvek drain wrap. It's got, it's groovy, so, right, Teresa? And if you look at Tyvek, which is basically a high-density polyethylene or drain wrap, you'll see that they're in the 90 degrees, or like almost, they're on that borderline to hydrophobic, right? But they're also relatively lastingly hydrophobic. That's a good thing about them. So I'll tell you why that matters. Notice the asphalt building paper, when it's new, it's really quite hydrophobic. If you leave it exposed to the sun for a while, it gets less. Like if you put it on a building for 6 months, it blows off. But it really reduces its angle as it flies into the neighbor's property. So the reason we care about these water properties is that there's attraction of the water to a material if the material is hydrophilic. So water will want to stick to it. And basically the angle is less than 90. And when we talk about cracks and pores, holes, there's a lot of surface area for the water to cling to, and especially small cracks and pores. There's a lot of surface area for the volume of water. And that interaction is what capillarity is all about. It's the interaction of that large surface area with attractive materials to water. So if I were to look at a test tube or a glass of water, like a real glass, of water. We have the glass with the silicon dioxide, and we have H2O. The positives and the negatives will be attracted to each other electrostatically. There's even a little bit of hydrogen dipole movement stuff, weird stuff. But it wants to stick. And that means that water will try and stick to the glass and drag the neighboring water with it, right? So one side it wants to stick to the glass, the other side it wants to stick with the water, and so it says, come along with me. And as a consequence, when you get close to the glass, you'll see a curve. And you can do this in your kitchen, right? You can see it, it's only a little bit, right? It's called, what's it called? Meniscus, right? I think they're changing it. It's going to be peopleiscus or something. But right now, it still is a meniscus. So mercury is equivalent of hydrophobic to glass. And so if you put mercury in a glass tube, you get the inverse curvature. On the right-hand side, these are relatively small tubes, about a 1/4 inch diameter, a little over a 1/4 inch thin-walled glass. So they're accentuating the curve. The curve is the same whether it's in a big glass or a small glass. It's just that when you put the sides close together, the curves intersect. And if you put the glass really close together, not only do they intersect, they drag the water up from below. There's mercury, there's balls of mercury, as that you can see the angle. So that front image I showed about the dentistry study, one of the things that is done in capillarity research is they have this sort of sheets of material, and you make a triangle out of them. And I'm showing you on your left-hand side, there's 2 sheets of glass, and on one side they're squeezed relatively tightly together in contact, and the other side there's a gap made, right? So on the left-hand side I got a gap. I'm now, on the right-hand photo, I've turned these 2 sheets of glass vertically, and I set them in the blue water, right? The blue water is a lot like water. And when I take it out of the blue water, the large gap has wicked up and held a small amount of water, or I shouldn't say that, a small height of water, and as you get to the contact surface, it's wicked up quite a way. So if literally it'll have gone up the 10-inch height of the glass, right? It's just such a little bit you can't see the coloring of it, but it will go 10 inches up the glass. So what this is saying, this is what the original people like Jurin observed, was that they knew that as the gap got smaller, the water was wicked up higher. Okay? And now that wicking up higher, what's causing the water? Why does the water wick up? Capillarity. What's causing it to go down? Gravity. Does everyone get that? Right. Okay, so no high school grads here. The water that curves like that, it's the balance of forces between the gravity and that capillary attraction of water to glass. Now, gravity is pretty important for buildings. I'm a big fan of respecting gravity. But there are other forces that happen, and those forces are, most of the time in this context, we're dealing with air pressure. So we're also going to look at both how gravity affects this and how air pressure affects this, because both of these things matter in the cracks that we are going to talk about. So, how much does it wick? That was a spelling mistake. How much does it wick? We can predict this with pretty good accuracy, but not perfect accuracy. So if you're looking for, let's say you're a judge, and you want to know how much the water wicks up to within the nearest 1%. You can't really, because the world varies by more than 1%. But we can give you a good estimate and try and put bounds to it. The good news is it doesn't usually matter. Like you just need to know it relatively close to make decisions. So when we talk about capillary suction or capillary pressure, we usually are using units such as pascals or PSI, depending what unit spaces are you on. But you can also report it as head, assuming that you're only interested in vertical. Because if I put it horizontal, gravity is not stopping it from wicking anymore, right? So if I take those 2 sheets of glass with the water and that nice exponential curve and I turn it sideways, the water will actually wick horizontally into the small gaps because gravity's not resisting it. So, but assuming that it is vertical, you can report it as head. So how many inches of head, or you buy pressure sensors in the HVAC business in inches of water column, right? That all, this is water in a vertical direction. So those are the units that I'll talk a little bit about. And also I mentioned capillary rise there, just so you got words that people use. Capillary rise assumes it's working in this direction, but it is actually working in all directions. It's just that's the one we're normally worried about. So here's the, I believe this is the only equation in the presentation, I'm pretty sure. So this is the Laplace-Young capillary equation for either gaps or circular tubes, and water and air. That's what this will work for others, but let's just say that's the equation we're going to use. We put in the surface tension, that sigma up there. It's a Greek letter, yes, Achilles. And that's what we use for the 0.072. And then it'll tell us how high. And so you tell me how big the crack is, I'll tell you how much it sucks. Don't quote me out of context on that. And so this is, in practice, a big challenge is that we often don't know how big the crack is. And in fact, when we're looking at cracks, as building scientists spend far too much time doing, the cracks are rarely a dimension, right? They vary, quite a bit. The other problem is that we don't know what theta is. We don't know the angle unless we're doing, say, water and glass or water and HDPE. But when it is water and 87-year-old cedar, it's a much more difficult theta to know about, right? So there's often, if you want to do a calculation, you often have to do a little bit of background to collect data on what's going on. So the small pores I have talked about in the past are the ones, like I say, in gypsum and wood and concrete and brick. And these things will wick water, and they will wick it often to heights of yards at the least. But it takes a long time. So here's a free takeaway, I didn't even make a slide on this, is that water flows through very small holes more slowly than through big holes. And when you have very small holes, although they suck a lot, they don't allow a lot of flow through quickly. It just takes a long time. So the smaller the pores, the more pressure, and so you can get yards of lift, but it's really slow. And so clay soil will wick water, 10 yards, no problem, but it takes a long time to put water through 10 yards of clay, like nearing enough to forever for people to use it to line, garbage pits, as an example, right? That's where we put our toxic waste, right? We rely on capillarity to not have it leak through the clay, that kind of thing. Whereas if you talk about sand, it only will wick water maybe a few feet at most. If it's good granular sand, only a few inches, but water will pass through that very quickly. So there's this trade-off. The cracks I'm going to talk about aren't any of those. My cracks are going to start at maybe the coarse sand and move their way up. The cracks you and I can see between building components or within panel products, etc. Yeah, go ahead.
How much of a factor is temperature of the material?
How much of a factor is the temperature? It's a non-trivial factor. I mean, it depends on what your accuracy is. But within the realm of normal building, the temperature of the water is actually more what I mean by that. Plus or minus 10%, plus or minus 15%, depending. And when you drop below freezing, it doesn't matter at all. Apparently you all figured out why. That's good. It's good. You're definitely not a graduate class. When we calculate these pressures, one of the most useful reasons to do this calculation is to get a sense of scale, order of magnitude. Well, Bill, you said, logs. I'm going to say order of magnitudes, factors of 10. Because as engineers, again, we'd like to get the right order of magnitude would be a good starting point. Scientists worry about the decimal point. We worry about not killing people and getting the right order of magnitude, kind of in that order. So if we look at the size of a crack of 1/2 inch, which I've helpfully put down in millimeters as well for people who are not from the United States or Bangladesh. I think there's one other country that still uses, but I'm not sure which it is. Anyway, it will wick up a very little bit. A 1/2 inch gap will only wick up 5/100ths of an inch. That's the curve that you're seeing at the edge of the glass. That's roughly the lift that you'll see. And that's equal to a wind speed, we're going to talk about how wind comes into this, of only about 10 miles per hour. If you look down to, say, a 1/16 of an inch crack, which is actually sizable in the world of capillaries, you're talking about a suction that might be 1.9 pounds a square foot, a head of 1/3 of an inch. Now this is glass, clean glass. How do I make it clean? Just so you know, I use alcohol, not that alcohol, but isopropyl alcohol, 99%. You wash it off, because when I touch that glass plate, my fingers, my greasy fingers, leave hydrophobic bits on the glass. Right, so you have to wash it first, just to say. Now, if you get down to really small cracks, let's say 1/100th of an inch, that's 0.01 inches. Now we're talking about water that can wick up 2¼ inches, which is equal to a wind pressure of 68 miles per hour directly onto that crack. Okay, so we start getting it up there. The next ones are kind of 1/1000th of an inch and 1/10,000th. That's the size of the pores in brick or gypsum or something. And those pressures start getting to numbers like 118 pounds per square foot, 1,180 pounds per square foot. That's how clay gets turned into adobe, right? You make it wet, you mix it up, you let it dry out, and it's held together by residual water, and that's why its compressive strength will be in the order of 1,000 pounds per square foot. Now, that's why you don't want too much coarseness in it, because that means it'll be weaker, but if you put too many fines in it, it's so strong it starts to crack, and you actually have the adobe breaks. So this is not about adobe, I'm just pointing out that if we were to talk about stuff like that, I would talk about adobe. But we're not going to talk about that, except to say that it should be obvious from literally a simple tabulation that porous materials like brick, gypsum, adobe, you can't make water leave them by blowing air on them. By the time you get enough wind pressure to do that, the building is in the next state. So you can't say, oh, the brick leaks. You know, people have said the brick leaks on forensic investigations. I don't think the brick leaks. No, I'm pretty sure it does. No, really, look, the brick leaks. Here, look at it right there. That's a crack. That's not a brick. That's a crack in the brick leaks. And that matters, because who are we suing? The person who made the brick or the person who made the crack? The person who made the crack. So, there are reasons to be precise about what's leaking. And even when we're talking about mortar, it's possible that mortar could leak if it were just really coarse sand with not enough cement in it. It's possible, but it almost never happens, right? Most of the time, it's the crack between the mortar and the brick, or the crack in the brick, or the crack in the mortar. Okay, I don't have to belabor the point, but I'm saying this is stuff that I see literally by national engineering firms in forensic investigations, and they tell me things like the water is being sucked through the brick by, wait for it, the HVAC system. I tell you, that HVAC system, it's running at a negative pressure of 0.1, and that, ever since we started these tight buildings, man, that's what's sucking the water through the brick. Which, again, like with just a little bit of this knowledge, you're going, well, that's obviously insane, right? But the problem is that that's not widely held under behavior, and so we're the heretics, and they're the sane ones. So, I'm going to start with talking about applications of this in terms of capillary breaks. I mean, everyone's heard the term capillary break, I'm assuming, if you're in building science. Sometimes it's confused with DPC, British DPC. What does DPC stand for? Damp proof course, right? Which is different than a capillary break, and I want to make that clear. Capillary break actually shows up in the Canadian Building Code. We actually are supposed to have one, and then it's incorrectly defined. But what is a capillary break? I actually couldn't find a good definition because most of the definitions I found described materials and such like that. So here's my attempt. A feature of an assembly that interrupts capillary flow. So capillary suction through materials or cracks or openings is interrupted by something. And I want to talk about the somethings that you can interrupt capillary flow with. So the one way we could stop capillary flow is to have a gap. And the reason that works is that small pores suck more than large pores, right? Everyone gets that? And a gap is just a large pore. It's sufficiently large to interrupt the wicking of the small pore on the top and the small pore on the bottom. It won't wick. And that means that that gap, just theoretically talking, could be quite small and it would interrupt. And some people think a capillary break needs to be a 1/4 inch, pick a number, 1/8 inch, an inch. And so that's not at all the case for almost any building material. Well, it isn't the case for any building material I can conceive of that you would need a gap that large. You need a gap, but it doesn't have to be big. So we're going to work through a number of reasons why I'd have a gap and explain what the size needs to be for each. Now, I could also not have a gap at all. I could have a great dentist and have no gaps. And the way to make that work is to actually seal off the pores so that it's not that the pores aren't too big, there are no pores. Right? So this is an impoverished material in that we've filled all the pores with some sort of goopy goop. And there's a lot of goopy goops available on the marketplace, right? And usually they're like polymers of some sort based on sort of dead dinosaur juice of some degree or other. And that fills the gap. And actually many of them work by also, they fill the pores. They actually have this job to try and get capillary suction be used to bring that material into the pore structure so that it bites in and holds on. Otherwise it could just, you'd paint it on and then it would just peel off, right? I'm sure you've seen products like that. It's not usually an advertised feature. So, but you can also have a large enough pore structure in the two materials that are touching each other. This is hard to do because unlike my drawing, there is a wide range of particle sizes and void sizes in real materials. So when you put two materials together, you have to make sure that there really aren't any small pores, otherwise it will join up with small pores. And it's hard to do that, but it's theoretically possible. Now, therefore, we have these three options. We can have an impervious material, a large voids, or we can have, I didn't show a drawing, I can also make it hydrophobic, in which case there's no capillary suction. So if you have hydrophobic materials, if you were to wax a material or coat it with a silicone or something like that, it would also not wick water. Again, the challenge with those coatings is that how durable and uniform are they? But they absolutely work, and as long as they don't get too polluted by dirt and decay, they will continue to work. So here, this is a plot. It's a bit early. It's not yet its 50th anniversary. This was published in 1974 by our very own Dr. Mark Bomberg. Where's Dr. Bomberg? I think he's around here somewhere. Right over there. Right. So Dr. Bomberg wrote a report. It's actually moisture flow through porous materials. There's a whole bunch of good shit in there, but no one reads stuff. So, but this is something I'm going to take out. And what he did here, and this was, I love this chart, Dr. Bomberg, because it's so indicative to people who are science-based to look at it. Takes a material and he either puts it in contact with a wet surface or he separates it by a 1 millimeter gap. So, the plot on the left is what happens when the material is put in contact with the wet surface. And in a matter of a few hours, the moisture content rises up, it gets saturated. We call that capillary saturated because all the capillaries are saturated. It's kind of weird jargon. And that's the moisture content it stays at. The two samples that are labeled number 2 for diffusion we put a 1 millimeter gap. So this doesn't mean that the material above doesn't get moisture, it's just it's not transported by capillarity. So if I put a piece of wood 1 millimeter above water, capillarity will not wet that wood, but vapor diffusion will. And so you got to know, and this actually comes up a lot in practical situations when we're dealing with moisture sensitive materials and built-in moisture content, is that, well, it doesn't take much of a gap to avoid water wicking across, but you might need to do something to stop water diffusing across. And that's where damp-proof course comes in. That's where we're actually applying a material that not only blocks the pores and is capillary inactive, it also has so few pores it doesn't let vapor diffuse through it in vapor form. Now, the thing about diffusion is it takes a long time, right? In this case, obviously Mark had a lot of patience. This was like running out to 2,000 hours, which is like 3 months. And so it must have been winter in Sweden. But anyway, so there was a lot longer to go. So this is an example of 2 bricks. Now the problem with time lapse when you take measurements is that it's hard to put them back in the same place. So this was not taken in California. This was just me not putting the piece of brick down in the right spot. But every time I took it out to get a reading, I took a picture. The camera was on a tripod, but the piece and you'll notice how it gets dark at the top, right? So that's water. It wicks into the bottom brick, and then it starts wicking into the top brick. And it actually didn't take long. I mean, by 24 hours, both bricks are totally flattened out and wet. And these are bricks are sawn finish. They were sawn out of a real brick, and they're just touching each other, okay? So no extra effort was done to ensure capillary contact. And when we did the test, Schumacher and I were going, well, I don't know, is it actually going to wick across the crack or isn't it? I mean, it's still kind of rough. We're kind of looking at it. It still looks like there's a bit of a crack there, but it contacts enough that it actually wicked up rather remarkably quickly. But so here is what we did to add a small gap. I didn't have a paper clip, so I used some telephone wire. So this is 28 gauge telephone wire with the insulation removed. And so that's the space that we're using as a gap. It doesn't block much of the area, but it does separate it. It is roughly a millimeter, a 25th of an inch, probably a 32nd, more likely, something like that. And so they were stacked on top of each other. You can see the crack is visibly larger. And now what happens is the bottom gets wet and the top doesn't, although we were wondering, okay, it should eventually get wet by vapor diffusion. But the problem is in this experiment, the brick is exposed to the lab atmosphere. So yes, water vapor is diffusing across, but it's also drying out. And so after 4 or 5 days, luckily my experiment came to an end and I didn't have to wait till the end of winter. And so this, basically it didn't actually show anything at all. It just stabilized and then it started bouncing with the RH in our lab. So which runs at 50% plus or minus 3%, something like that. And so I was noticing, oh, it's starting to pick up 1/100 of a gram. Oh, it's down to 100. So I wonder what's going on. And oh yeah, the RH is varying a little bit. And so that's the only reason it was moving. So when I plot the moisture versus the square root of time, why the square root of time? Complicated mathematics, but the square root of time is what's done. The bottom brick I'm drawing in the, showing the red, but really it transitions at the start of the green to the next brick. It does soak up until enough points of contact are actually connected to the brick above, and then it starts feeding the brick above. And then actually the brick above got wet because it's the square root of time. It took a bit longer, like 3 times as long to wet the brick above than it did to wet the brick below. But it got there pretty quickly. Whereas when we did the other one with the little gap in between, the bottom brick gets wet, and then the top brick just bounced around, like I said, a few hundredths of a gram up, a few hundredths of a gram down. A gram is a small unit of mass for those of you who aren't. Okay. So what did we learn from this stuff? Capillary wicking is stopped by a capillary break, and the gap size could be really small. And I'm saying a gap of 0.04 inches because I tested it. I didn't test the 0.02, but I tested the 0.04, good enough. Right? That's good enough to be a capillary break. Doesn't stop vapor diffusion, but it stops. So depending on what you need in your design or what you're trying to understand in an assembly that's working or not, that's sort of all you need to stop capillary flow. So why then do we often put bigger gaps in buildings, particularly behind, say, cladding? Why do we put bigger gaps? Well, the first thing is we know the answer is not to make it, we don't need a 1-inch gap to make a capillary break. We don't need a 1/4 inch or 1/8 of an inch to make a capillary. So there's got to be other reasons. So let's look at what some of those reasons might be. Well, the next reason we're going to dig into is we might be trying to avoid bridging of the cavity. I'll describe what I mean by that. But then we'll look at also drainage. Another reason we might want a gap is that, hey, we want to encourage drainage underneath this roof membrane or behind this vinyl siding. So that's another reason we might have big gaps. So when we talk about bridging, I'm looking at something like this scenario. On the left-hand side, I have water running down the backside of a cladding. And those little droplets there are drawn because that's kind of what the droplets look like. I'll show you photos in a bit. If the gap gets smaller, eventually the water droplets running down the back of that outer layer are going to touch the inner layer, and actually happens very fast, even at 60 frames per second. It's like 2 frames, and it goes from a droplet to a plug of water. It's just boop, and now it makes that plug. It doesn't make that noise. I know it doesn't make the noise. One of the things that I'd have this drawing around for a long time, but I didn't know what the size of those droplets were. But I've asked people, where's Mishka? I've asked people, how big do you think a water droplet is running down? And most people have a kind of a good idea. It's not that big. So I always knew that we don't have inch drainage gaps behind cladding to stop water drops bridging across. Right? If the droplet is that big, you're not on the planet Earth. You're in a much lower gravity scenario. And then it'll get bigger, but that's not what we're dealing with on Earth. So the strategy we took in terms of measuring the size of water droplets on a surface is that we measured the water droplets on a surface. To start with, we started again with glass and then went to HDPE. So the glass is easiest to photograph. So you'll notice also the water dripping off the bottom, but eventually if you put enough effort into measuring the droplets, you'll be able to figure out how big of a droplet does it take before it runs down. Not in this presentation, but it depends on what the surface is, right? But it is actually pretty definable number for a particular surface. It's a particular size. The hardest part of those experiments is making sure that the needle, that you don't vibrate too much because of the excitement of it all. So here's some examples. This is a water-resistive barrier on the left-hand side, a peel and stick membrane with an HDPE facer. See the droplets? They look just like a droplet. And this is looking from the top. You take a photograph, highly zoomed in, focus there, and this particular drop, the one in the middle has already fallen down. The one on the left is the one that's hung on the glass. 2.6 millimeters, plus or minus 0.1 millimeter. Depends a little bit on whether what the material is, but it's almost, I've never measured a drop more than 3 millimeters that wasn't moving. So if you juice it, you can get a bigger drop. But the water droplets generally are under 3 millimeters, which is less than 1/8 of an inch, right? Just in case you're wondering. So now that you know that, you can go home from summer camp with your $1,200 well spent. What we do know, though, is gaps over 1/8 of an inch won't bridge. So if we're worrying about water bridging from one side to another, 1/8 of an inch is going to be enough. Plus, of course, dimensional variations due to construction and operation and so on and so forth. So with brick, that would be 2-3 inches. That was a bit of a joke there. But really the question is, why do you even want to stop water from jumping over the gap? So there is discussion in even code committees and stuff. Oh, we want to stop the water from jumping over. Why do you want to stop it from jumping over? Because when it jumps over to the other side, what's it going to find in most walls? WRB, right? I mean, so you'd be insane not to have a cavity wall without a WRB on the other side of the cavity, right? And rely on the gap, because the water's going to get across at windows and doors and pipe penetrations and wire ties and cladding attachments. Now, I say that you'd have to be insane. Let me introduce you to the continent of Europe. So in Europe, it is absolutely still considered normal that you design the cavity so that water doesn't come across it, and you don't use WRB. Now, they're starting to, has to do with building failures, but they're starting to. But it also has as much to do with building failures of what type. They are moving to a lightweight building system because of environmental, economic, resource things. They're moving away from, the standard 2 feet of rocks into, how about we use like wood studs with some OSB, right? But yet, seriously, papers are being written in the last 5 years in peer-reviewed European journals about, so do we really need a building paper behind a wood cladding on wood framing? Serious questions being asked by serious researchers, just pointing out that there's still a lot for us to talk about. And the worst thing is when they import their products, because they come from Europe, they're of course superior. But they became expensive, and so of course when you buy them, they are superior. They came from far away, and they're expensive. And so then you look at the guide, and it shows no WRB, and so then the architect dutifully draws the system as per manufacturers. I mean, how could the Germans be wrong, right? And of course, most of the time this problem is caught in drawing review or when a contractor looks at it and says, WTF? But I'm pointing out, this is how serious this disconnect is about the role of bridging and droplet sizes, and it actually pervades into, I can show you dozens of manufacturers' instructions from Europe that do not require WRBs behind like really leaky claddings. Unsealed joints. But hey, look, you got 2 inches, you're good, right? Said no one ever. So it might not be about the bridging, but here, let me give you an example where it might be about the bridging. I think we've cut off a little bit of the slides here, but some of you may be able to see them. On the left-hand side, we have a zinc roof over a black entangled mesh, I think is a generic term for that, right? On the right-hand side, we have a painted metal over top of a peel and stick membrane. So why do people put the entangled mesh under some metal roofs and not put it under other metal roofs? So hopefully you can, if you know about roofs, that metal on the right-hand side, it's pretty much directly in contact with the peel and stick membrane, right? You're putting a screw through it, or you have a clip and snap it on, right? And it's going to be in touching the WRB at a lot of locations. The reason that they have that entangled mesh is that apparently they don't want it to touch. Now, the most common reason, if you were asked this in a normal setting, they would say, oh, that's to ensure drainage. But actually, we'll find out later, no, it isn't, because you can drain plenty of water through the system on the right. So, if normal system without a big gap, without an intentional gap, is that the metal moves around a little bit, there are laps in the peel and stick membrane, and so there are spots where it touches and spots where it doesn't touch. When water gets through the metal, and it doesn't get through the metal, does it? It gets through the joints in the metals, the screw holes, you get condensation sometimes, but it doesn't get through the metal, let's be quite clear, right? It's like people saying, my metal's sweating. No, it isn't. It has not become a mammal. It is not. It's still an inanimate metal. so it's not sweating. And it also, water doesn't go through it. It goes through cracks, holes, and openings. So, but the water gets there. We know that. And it results, not a lot of water, and so you end up with little droplets of water. And small condensation quantities, like night sky radiation induced, or small leaks that occur in metal roofs are small enough that you end up with droplets. And what happens is you get corrosion, localized microcell corrosion between the wet bit and the dry bit. Excuse me if I'm using too much jargon, but that wet bit, dry bit transition allows for a little battery, not a good, you can't drive a car, it's just a little battery. If there's any VC people in the audience, no, you can't drive a car. All it does is it creates enough electric current to cause corrosion. Now, it doesn't happen on all systems, and I'm not even sure that we know why it doesn't happen on all systems. I know that a normal painted metal, the backside is painted. And that means that it's actually protected from corrosion. We have the problems we do know occur in copper and zinc. Haven't seen it in titanium yet, but then we don't do a lot of titanium. But that said, maybe it's susceptible. I wouldn't think so. Titanium's pretty resistant, right? But this is a zinc roof with a touch of titanium to give it that dark color. A company you probably all know of. It's a national leader in making zinc roofs. And so they had money left over on this project, and they're saying, hey, how about we give the client a much better roof? So they upgraded from a 2-ply SBS bitumen, which probably only had a 40-year lifespan, and they said, we're going to give you a solid zinc roof, and that way you'll get 60, 70-year lifespan. So then we got a call a couple of years later, and it's like, we have water coming through the roof. And well, how do you know? You've got a peel and stick membrane. Well, okay, we have water dripping out.
We send up our maintenance people, and they see holes. Like this. I didn't take these pictures. They took these pictures. And they say, oh, what's going on? It's like, well, I don't know. What do you have underneath the zinc? Well, and here they go. And I said, well, you idiots, you didn't provide a gap underneath. Well, no, we just copied it right off of manufacturer's drawings. And they don't have that. They have the zinc roof direct applied to a WRD. Okay. Now, we've only known this is a problem for maybe 20 years, so I understand it takes a while, but the Midwest is not that far away. It's not 20 years away, except when it is. And it's not just the Midwest. We've also had, this is another zinc roof. So this is a rich person's house. RPH is a rich person's house. Apparently some people don't know that. So it's a rich person's house. And this is actually in a relatively dry climate in Texas. And this was a few years later. But one of the nice things about this picture, if you're not the owner, is the wrinkles. Can you see the wrinkles in the WRB and how where it held up in the water, you got the corrosion, you know, like, so even before, like, you don't even have to, like, go there and take the roof off. Of course you do, because you got to rack up the bill. But really, you pretty much know that this is another one of those. And there are, like, in the last 10 years, I've even worked on or heard of dozens, and many of them are quite large, like, you know, 500,000 square feet in Chicago. And they happen quickly, under 5 years. And you get holes through. And, you know, so the first answer is, well, we'll plug that hole up. We can just solder on it. Yeah, you can. But you're just going to come back next year, and the year after, and the year after. So the only solution is, of course, the expensive one. You take it off, and then you put in a gap, and you put it back on again. And usually it is not the same it as the first it, which adds the cost of it. So that's the reason why we want a gap. And this is one of the few examples of when I had to start planning. When do I care about bridging? Oh, look, I got something I care about bridging. Finally, something where I give a shit about bridging. So I don't want the droplet to be able to hang on the back of that zinc. So by making a 3 millimeter, 1/8 inch, or a little bit larger gap, I can be pretty confident that I won't have water droplets that are long enough hung around on the metal to cause local corrosion. This is all about liquid capillarity, but the point being also, look, diffusion's going on here. And another reason you put that mesh in there is it's going to enhance air exchange, which will provide convective drying, which depending on your details could be significant. Notice the building, I'm looking at the photograph there, that is a really long chunk of zinc. It's not going to get much ventilation at all from an entangled mesh. More than nothing, but probably not meaningfully more than nothing. So all of those mechanisms, drainage is still working, convection is still working, diffusion is still working, but yeah, I'm choosing examples where capillary has a dominant influence that's worth noting, worth talking about. So drainage was the other example of things we could talk about. And so we have a lot of enclosure systems that have rely on drainage, like T111 siding, you put T111 or LP Smart Side, you apply it direct over the WRB, or fiber cement. I looked up a fiber cement manufacturer that does this. That's Nishiha in this example. We use eaves, let's say stow eaves, right, John Edgar? So that's where you're using grooves of adhesive to form a gap. And at the beginning of these, when these were first introduced in the 2000s, there was a lot of people going, oh, bullshit, you can't drain in a gap that small. And they said that because they never actually poured any water in a gap, right? They just said, you can't. And by the way, those people are still alive. And they're still, I still run into them. And they say, oh, come on, an 1/8 of an inch gap, you can't drain water in there. So have you poured water in the gap yet? No. Well, but lots of people have. That's the good news. We've moved forward as a society, and people have poured water into small gaps and watched gravity do its magic. So there's a penny there. You can't see that it's a Canadian penny, but you're going to have to trust me. It's about the same size as an American penny. So let's look at some of the historical research on these small gaps. You'll recognize, I think, if anybody recognizes the guy who's photobombing in the upper left, I'd like to know who he is. Teresa, I think he was a local DuPont rep or something like that. But anyway, the other people I think you'll recognize, except they were younger then. So Bill Brown worked with the United States Gypsum Company, and they did publish a couple of papers, 1999-2000, where they looked at small gaps behind stucco and behind exterior insulated finish systems. And Teresa gets a call out because actually you're the first other paper other than Bill Brown's where you talked about the development of, at the time, stucco wrap, which became drain wrap, which was the crinkle. And so those were like investigations, laboratory type investigations of tiny gaps, pouring water in, seeing how much came out, asking the questions, is that enough? And that's why most of you will know drain wrap being I'll show you a picture later on, but it's not a lot, it doesn't have a lot of big gaps, but it drains like the dickens, right? It really lets water through. This photo is taken as part of the JJAC project, and JJAC stands for John, Joe, and Achilles, and that was the hut, because we didn't want to say the ja, so we said ja, JJAC. Oh no, maybe the C was Mr. Schumacher. So that's where so you don't see Achilles in this one, but Chris is the man with the white shirt. Joe is obvious. Koda Ueno, who's still around, I think you're here today, Koda, he's certainly around all week on the left-hand side. And Marco Liberte, I don't know if he's here, I haven't seen him yet. He's here, all right. But this was actually, we built a test hut. And this was during summer camp, so, this summer camp, we, opened the outdoor air dampers to fix the building. This summer camp, we started building this turret with gun ports, but actually, those ports were actually intended to be able to inspect the back of the clad. And so you'll see Andre Dejourlay there in the blue shirt. He's directing he's got his hand up, directing the research, as he still does to this day. And I'm carrying the whole weight of the project on my shoulder. Chris is trying to stop, who's in the gray shirt, trying to stop me from falling down. So not much really has changed, except us. So this is 2 layers of building paper behind a stucco cladding. And I hope you can see this from the projectors, but we poured water at the top, and we expected water to drain between the 2 sheets of paper, but it was astonishing to us that you were literally pouring the water in, and it was coming out. And so that was, people had kind of surmised that, but, with the proper budget and a crack team of high-level computer modelers, we were able to demonstrate that that water did flow through small cracks. So Now, this is now, I'm going to show you a couple of experiments where we take 2 sheets of glass because they're transparent, put water in them, and then you can watch the water droplets fall down. And I hope what's clear here is that at the beginning, water droplets are shaped like this between the 2 sheets. There's a curve at the top pulling up. There's a curve at the bottom pulling up, holding that weight of water. And as soon as I add enough water, the meniscus doesn't get any bigger, right? That curve is still there. The contact area is the same, but the weight of the water gets up. So eventually I make the water droplet big enough, the weight must overcome the adhesive forces as I'm not making it any bigger. Now, if I add water and the droplet gets wider into the screen, oh, well then the adhesion is stronger because there's more contact area, but the weight goes up and you might be imbalanced. That's complicated. Does it get fatter or does it get higher? What happened? Shit, who knows? And so you do some experiments to find out something. And I want to point out that the gaps that I'm going to look at in the next few are like 0.5 millimeter, which is 0.2 of an inch. Then we're going to look at 4/100ths of an inch, or 1 millimeter, and then around a 1/16 of an inch. Those are sort of the gap sizes we're looking for because we're talking about drainage in small gaps. Or other, let's be clear, I'm talking about drainage in small gaps. So I'm going to make this go away somehow and show you, say this one. So this is just to get you a little bit more in the dynamics of it, because it actually does matter where I'm putting droplets of water, they're running down. The first thing to notice is that the water runs down pretty reasonable. It's not like at an automotive speed. It's running down, and also it's not running up, right? Because the gaps are holding on to it, and when it gets to the bottom edge, the water is clinging to the bottom edge, and that gives it a little extra adhesion so it doesn't fall. And then, unless you get enough. Okay, so I'm going to squirt a bit more in there. And then, oh, look at that. Oh, did you see that? That was exciting, eh? So there are endless replays, and then there's the director's cut you can buy. And you'll see that now, if I put the water in slowly, it makes the droplet get wide. If I put the droplet in fast, momentum punches it through and it drops. So, oh, I made it too good. Ooh, and it goes through. And then we'll watch this for a little trick. Yep, capillary suction. The pores in that napkin are much smaller than 1 millimeter, and so, of course, it sucks all the water out of the crack, right? And one of the challenges of this stuff is how do you make sure that you know what the gap width is? If you can barely see those metal strips, those are from feeler gauges that are taken apart, so they're quite precisely 1.00 millimeters. And the glass is lap glass, so I know it's flat to within pretty good tolerances. Not perfect, just good. And so what we can take out of that is that with that size of gap, the water that's stuck on the bottom, you can see, is pretty small, right? A little bit of water was retained, but also water will go through that, like almost like poo through a goose, right? It's pretty, you put some in at the top and it comes out the bottom. It's only a couple seconds here, goose couple minutes. Now, we might be able to simulate fiber cement as if it's glass, but it's not reasonable to simulate Tyvek or peel and stick as glass. So the next sort of one is going to be, we're going to use high-density polyethylene sheet, relatively thick and flat, and I'm going to show you a bigger gap, just to give you a different flavor here, because everyone wants flavor with their gaps. So here we are. Just to give you some dimension, there's a water droplet that I put in that was barely the right size. And so there's a bit of a trick about ejecting droplets that are big enough to roll, but not big enough to roll right on through to the other side. Right? You don't want the doors droplet. You want to have the right side. Okay, there are the doors. But anyways, so if you put more on it, then it obviously will jump through. But you see the shape of the droplets, and then, again, I do the trick of wicking it up. So look at how much water is retained in a 1.5 millimeter gap with an HDPE, hydrophobic, on the outside, right? The answer is nothing is really held in the gap. It's just water on the surface. right? So that the 1.5 millimeter gap, which I forget is about a 16th of an inch, and you're not really storing any water at the bottom. So maybe a 1/4 inch, and you saw that sometimes it would move sideways, and there was a bunch of variations. So the next thing I'm going to do is use a small gap. We started with 0.04 inches, and then we went up to 0.06 or 6. Now I'm going to go down to half the size. This is 2/100ths of an inch. This is much smaller than you would gap a spark plug, if anybody knows what a spark plug is. Sorry, you're not my graduate students. Yes. So, is that an Uber? So, anyway, so here we have, this is now pretty small. Now look, that droplet, I have to make it pretty big because there's lots more attraction, I have to make it a little bit more. And so it takes, and it also is hanging up at a higher level. So you can see, I'll get some water draining out. There's the droplet on the right side at the 2-inch mark. She dripped. But so that tells you roughly, maybe, it's not really a 1/4 inch, a 1/2 inch, and we'll call it a 1/2 inch. So that's with a really thin gap, just so you know. So when people say, when I show the photograph of that east with the 1/8 inch or more crack, not 16th, and people say, oh, come on, surely that doesn't drain. It's like, surely you've never done it before. That's all I can take from that. It should be clear that a gap that size can drain a lot. And now we're going to talk a little bit more about, well, is that the reason we're making gaps? So it does retain more, and we learn from these videos and many more, if you get the whole DVD, if you have a DVD player somewhere. That look, water can drain in very small gaps, but people don't seem to recognize the importance of it's the opposite. It takes a very small gap to let water in. And so if you have a crack between an aluminum trim piece, say an aluminum extrusion on a curtain wall and a snap aluminum extrusion onto it for a trim, that crack's in the 0.02 inch range. Those cracks will actually wick water in, and they will leak enough to be annoying to some people who like dry. And the gaps will retain some water, but actually the quantity, because the gaps are so small, is very, very small. And I didn't show you, but I've done also measurements where we've actually measured how much water sits on flashing. And short answer is the water that would sit on aluminum flashing, literally order of magnitude more than would be retained in a small gap at the bottom because of capillarity. So if you're worried about water being retained, I'm not. So we'll be talking here the air gaps and looking at walls primarily in this image. This image, I think, was mostly drawn by Graham Finch of RDH, and this is being done for RAINA, the Rain Screen Association of North America, trying to define what is a rain screen after all. And so there are systems that have gaps that drain. There are systems that have gaps that don't drain. So you got to know which you're dealing with. They also have gaps that are large enough to stop bridging. We have gaps that are large enough to allow ventilation drying, which could be quite important. And then we have gaps that are large enough that they can spread fire, large enough to house pigeons. And so at some point you want to say, so how big do I want to get? Do I want to encourage fire to move up the building? Buy a European cladding system, because they provide, they got a good 2-inch gap, maybe 4, depending on the model. And yeah, that's a good way to spread fire. Okay, and at the 4-inch level, yeah, that's not only enough for like pigeons. I mean, that's where you can start providing housing in New York City. And so the gap sizes that are not, it's not always more is better, or it needs to be bigger, or there are real functional reasons for gaps, and there are pros and cons that we need to balance to get the best outcome. Anyway, so here's that Tyvek drain wrap. On that image, you wouldn't think it would provide much range. The hidden secret, I'm not sure if it's a secret, Teresa, but not many people seem to know, is that the plastic-headed nails you use to attach that to the wall provide a really big drainage gap. And so I've often wondered, how well does this drain in actual job sites? It's like, well, every time it's like the freaking nail heads that are providing the gap, and it drains like the dickens, right? But you know, in the lab, you can not use the nail heads, and you can show that it drains really good. We also use dimple sheets. Often gaps are 1/4 inch, 3/8 of an inch, and below grade, but again, real track record of practical performance, make a fundamental difference. Way better bang for buck than any waterproofing product you can buy. But in the gaps, do they need to be 6 to 10 millimeters? No. But if you want to make a sheet with the physical properties that dimple sheets come in, they end up being 6 to 10 millimeters thick. And again, people think, oh, it has to be that big to let the water through. No, unless you're draining Niagara Falls. Then they probably need to be bigger. But if you're not draining the Hudson River through your foundation, you can probably get away with smaller gaps. So we're also seeing these gaps come into behind stucco. Now, the gap that we currently have behind stucco in the code is 2 layers of building paper, right? Or maybe a building paper and a drain wrap or something like that. That's a pretty small gap. And so the code requirement is moving in wet areas to increasing the space. So have you read any of the reports about why that's being done? Have you seen the physical tests of real buildings? No, because there aren't any. But it doesn't mean it's a bad idea. But the gap is not likely to do much for drainage. It is likely to help with ventilation drying, even a little bit. It is likely to limit the amount of bridging from the wet stucco side to sitting on the WRB. And some WRBs don't like having water sit on them. Let's say they were made of, say, paper. Then you might be worried about long-term exposure to water. And so this is almost certainly an improvement in performance, but you can't argue it's because we needed more drainage. Because there's not really a lot of evidence for that. So, but it's coming to our code. Now let's talk about, in the last 10 minutes I think I have here, is that right, Joe? Yes. Okay. So many of you must have seen this image of rain penetration, right? And one of the rain penetration modes is pressure-assisted capillarity or air pressure differences. This is right out of Canadian Building Digest and various documents from before I was born. So here's an image from New Zealand, and they're showing an image of a aluminum window extrusion and a very angry-looking wind that blows upward. But they're upside down, right? So you know, on the other side, so you got to give it some sort of, flexibility. So, but what's really neat is it's showing how each of these mechanisms actually can play a role in a practical scenario. Sure, this doesn't look like a modern window for us, but it's possible that water could blow right into the gap where it says number 1. Gravity would drive it through the joint between the 2 pieces of aluminum. It would come through at number 2 for the gravity drainage, and then it would go sideways by surface tension along the underside of the aluminum. It's very practical. We see this stuff in the field. And then if there's a gap between the concrete wall and the aluminum, wind could blow it horizontally, and capillarity could suck it into that crack. Those are all practical. In 5, gravity drainage would take it down the rest of the way. So when we're often talking about multiple mechanisms, often in series, but sometimes in parallel, right? So just when you talk about capillarity, it's not just about capillarity, there's a whole bunch of other stuff going on. So here's some examples of gravity-assisted capillarity. Water is whipped in the capillarity, which in the height of that elbow could be as much as we calculate with that equation, right? Half an inch, something like that, depending on solve that. And the downward leg has to be longer. That's the key. You have to have the downward leg longer than, if anyone's ever siphoned gas in a car, to be helpful to somebody, you'll know that you gotta get the tube down, and you'll know you don't want to suck any of that into your mouth. The latter lesson has nothing to do with building science. So the other one is that water could be whipped into a gap, and then wind pressures could push it out, right, and blurb it out the other side. So this is an example of capillarity, and to get capillarity to go over the edge of the cup, you need to use pretty small capillaries. So that's why we use the napkin, right? So a napkin, you can do this at home. This is actually something that's done a lot for children's science shows, and it's quite effective. And it's actually the Rainbow Coalition of Gravity Supported Siphoning, and you'll see that the colors will change. Now, because it is small pores, thousands and thousands of small pores in this napkin, this will take hours, not minutes, it will take hours. But it still will move a whole half cup of water in a matter of 2 to 3 hours. If you want to move more, you need to use more napkins. Or if you want to move faster, you take the cup and you pour it in the oven, just in case you didn't know. Now, this actually has a kind of a version of this is pressure-fed gravity-driven capillarity. The crack on the outside of the brick veneer wall is going to be on the vertical joint, because the mortar will shrink relative to the brick and it'll separate. The horizontal brick mortar, it'll also shrink, but the weight of the brick will keep the crack small, right? Though the brick doesn't end up floating in space, no. So it squeezes down, whereas on the vertical, it opens up. And when that happens, water can wick in, and those cracks are exactly in the range I'm talking about. Literally in the 0.02, 0.01 inch, up to 0.05, 0.06. By the time they get to 0.1 inch, people call them deficiencies. But below that, they're just normal. And when you apply air pressure across the brick, first of all, when you put no air pressure across the brick, you spray water and water starts flowing through. And that's whipped in by capillarity and pushed out by the head of gravity of water that build up. I'll show in a moment. But you can actually calculate the average size of the head by applying negative air pressure to say how much pressure do I have to push back to stop water from leaking in. That's what this experiment's about. And so in this particular brick wall, minus 125 pascals, or a little over half an inch of capillarity, was the average size of the vertical height that I'm showing on this drawing. So the crack wicks the water in, and the difference between the highest entry point and the lowest exit point is what builds up head. And if there's enough head for the crack size, water will come out by gravity. And when you're doing spray tests, you'll often see the water blur out. And that's because it's filling up the crack, it reaches the head, it overcomes capillarity on the inward side, it leaks out. So you get like a little bit more blurpy. So you gotta spend time staring at your brick walls during tests and not just saying, okay, failed at 15 minutes into the test. It's like, experience the moment a bit more. Look at the blurs. So finally here, I want to take a look at how air pressure affects capillarity and how they can interact. And I can do this by looking at lap siding. Everyone knows about lap siding. It's used in many materials in many parts of the world. Here I have some opportunity to show another picture of Joe. I think he's a little younger than. This is a problem of lap siding in Cleveland that was published. It's actually well before we met. And I read some of Joe's stuff well before we met, because we were reading stuff in building science. And you can see water would be held at the lap and would start to cause the siding to decay. And one of the solutions to this, and this is not just for this project, this is relatively widespread in the Northeast for a while, was the cracks were so small because they were all painted shut and the wood was nicely smooth and fine, not like the old shit, all those bumps and grooves, that shit worked. No, we have an improvement here. This is nice and smooth and it won't work. And so then you could buy little wedgies and put them up here. These are not the ones you did in school. These are the ones you did outside. And that gap both reduced the amount of water that would wick in because it was much larger, and it enhanced air movement. And both were quite important to solving these problems. So the last video I want to show is something we spent a fair bit of time on, building this little box, getting it to work. And it's basically a little box with glass lap siding where we can apply air pressure and drop water on the back side. So we have water draining down this wall system. coming upon a 1-inch lap, and we can impose different air pressures on it and see what happens. So here if you look at the gauge on the bottom right, you'll see the air pressure stolen off of Minneapolis blower door, by the way. So I know Colin's going to be happy that I did that. Anyway, and so here we are, we're building up the air pressure and we're injecting water. The gap is only about 1 millimeter, exactly 1 millimeter, and you can see the water builds up, but now that I've got air flowing, air is blowing around the droplet of water, keeping it more narrow, and also turn the pressure down. See that? See the water ran up? Isn't that cool? I missed it? Yeah, I thought you missed it. Yeah. So, okay, here I'm going to turn the pressure down. Oh, and it relieves itself. So you'd asked earlier about whether we're going to see the relieve yourself images, but here we are. So here comes the pressure off, and everything feels good just to watch it run out. And so now I'm going to build up the air pressure again, and now if I get the pressure too high, you're going to blow the water through, and this is not as simple as people say, where, well, I have hydrostatic pressure, and then I have air pressure, and it overwhelms. The pressure in these systems, the air blows around it at much lower pressures than your calculated number, and it takes water droplets. Now, do I care about the water droplets? Depends on the system. But to be clear, it's not, oh, here's the capillary head, which should be about 25 millimeters here, and it should build up to 25 millimeters, and only then will the water come over. If you don't control airflow, it's going to blow air up the backside. And who wants air blowing up their backside? So on that high note, I'll say that we can end with some conclusions here. Very small gaps do act as capillary breaks. They stop wicking. An 1/8-inch gap will be enough to stop bridging across from one side to another. Very small gaps allow drainage and penetration, literally at the scale of, a millimeter would be fine. A millimeter and a half is probably pretty good to add a little bit of safety factor in there. But if you see a system in the field and it's like a 32nd of an inch, you can't say it doesn't drain. You now have to say, well, it does drain, because we know that it does. We didn't get into a lot of how these laps and upstands works, but really you do want to make sure that you don't have big air leaky holes, because the air will blow through screw capillary, it'll just drag the water droplets through. And so air barriers, I think most people know air barriers are more than just an energy and indoor air quality thing. They also are related to rain penetration, is that you do need good air tightness to avoid that. So that's why we don't want leaky buildings, right? We want good air quality, hopefully provided by a well-designed ventilation system, because leaky buildings just mean they leak air and water, as well as pollutants and all the rest. Okay, Joe, I'm sort of done.
You crack me up.
Well, you suck.